Hello, everyone. In this video, we define three important subspaces that are associated with a matrix. So we fix an n by n matrix, and it will be fixed for the rest of the video. The first space that we define is the null space. The null space of a matrix is the set of vectors inside Rn such that when you multiply them by the matrix A, you get the vector 0. In other words, the null space is the set of solutions of the homogeneous linear system Ax equals 0. Let's have a look at one little example. If A was this matrix here, then we could, to find the null space, we can solve the associated homogeneous linear system, Ax equals 0, which leads us to a reduced row echelon form of this size. There's a row of zeros. In other words, the fourth column denotes a free variable. And when you write down the solutions for this homogeneous linear system, you see that the solutions are just the value of the free variables times this vector here, because, for example, from the first equation, we get that x1 plus 4/3 x4 is equal to 0. In other words, x1 is minus 4/3 x4. That's how we get the first entry here in this solution. The other two entries are the same, and the fourth entry is just equal to x4, which is a free variable. The null space of the matrix A is the span of this vector that we found here in the solution. In fact, all of the solutions are multiples of that vector, and the span of the vector equivalently is the set of solutions to the homogeneous linear system. It is a subspace of Rn because spans are subspaces, and this is the span of a given vector. We can also check directly that the null space is a subspace of Rn using its definition. To do that direct check, we have to remember the three conditions that are satisfied by a subspace. First of all, we need to check that the 0 vector is in the null space, but that's true because if I plug in 0 here, every matrix multiplied by the 0 vector gives me the 0 vector, which says that 0 is a solution of a homogeneous linear system. If U and V belong to the null space of A, then this means that A times U and A times V are both 0. Therefore, A times U plus V, by the distributive law of the matrix product, is equal to AU plus AV, but that's 0 plus 0, which is 0. In other words, U plus V is also in the null space of A. The last check is that if U belongs to the null space of A and sees any scalar, we want to check whether C times U belongs to the null space of A. And the way we do that is by just multiplying A by CU, but by the properties of the matrix product, we can factor out the constant, and this says that the result is C times the 0 vector, which is again 0. We didn't have to check these things because we know that the null space is a span, as we said in the example above, but it's instructive to see how the properties of the matrix product help us check directly this proposition. At any rate, the null space is a subspace of Rn. The next space that I want to point your attention to is called the column space. Given again the same matrix A, m by n, the column space is defined as the span of the columns of A. So we don't need to prove anything because by definition, the column space is the span of some vectors, and therefore it is a subspace of Rm. Every column of A has as many entries as A as rows. So the column space will be a subset of Rm, a subspace of Rm, while the null space was a subspace of Rn. Here's just a little example. If this is the matrix A, then the column space of A is defined as the span of the vectors that make up the columns of A. 1, 3, 0, 0, 1, minus 1, 2, 0, 0, 1, minus 2, 3, and 2, 2, 4, 4. Another space that I should mention is the row space, which, as you may guess, is defined as the space obtained as the span of the rows of the matrix A. If you think about the operation of matrix transposition, you can probably see that we can relate this space of span of rows to the span of the columns of A transpose. In fact, the row space of A is the same as the column space of A transpose. Let's have a look at that in this example here. Suppose I write my matrix A using row vectors, R1, R2, R3, and R4. Then by definition, the row space of A is the span of R1, R2, R3, and R4, which means that all of the elements in the span are vectors that are linear combinations of R1, R2, R3, and R4. But the span of linear combinations of these vectors is the same as, I will write one more step, is the same as the set of vectors that are obtained by multiplying the matrix whose columns are R1, R2, R3, and R4 times the vector X. And the matrix whose columns are the rows of A is exactly A transpose. So the row of A is equal to the set of vectors V, such that V can be written as A transpose times some vector X. That's all for today. I'll see you in the next video.